Hello everyone and welcome to Control Engineering and Control Theory tutorials. In these tutorials we present real and applicable knowledge of control engineering, machine learning, optimization, robotics, mechatronics, etc. In this control engineering tutorial we explain how to manually construct, or better to say, how to sketch by hand a root locus diagram of an open loop transfer function that you can see over here. But before I explain how to construct the root locus diagram by hand, I need to provide the answer to the following question that some of you might ask me. And the question is the following one. Why do we need in 21st century to learn to construct by hand a root locus diagram? Here is the answer. By learning how to construct the root locus diagram by hand, you will obtain a very precious intuition and feeling on how the stability properties of the system change when you vary the system parameters. Furthermore, the root locus method can provide you very useful insights into how to stabilize your controller or how to improve the performance of your controller. More about these topics in my future videos. For the time being, in this video we will focus on the rules for constructing the root locus by hand. But before I start, I would like to mention the following. It took me a significant amount of time, energy, and effort to create this completely free video tutorial, as well as almost 300 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, let's start. The construction process consists of several steps. And here's the first step. In the first step, we need to recognize the poles and zeros of our transfer function. Then we need to mark or draw poles and zeros on our diagram. Let's start with poles. The poles are the zeros of the polynomial in the denominator of our transfer function, and the polynomial is s squared. Consequently, we have two poles. The first pole is at p1 is equal to 0, and the second pole is at p2 is equal to 0. How about zeros? There are two types of zeros. We have finite and we have infinite zeros. Let's first find the finite zero. Our finite zero is the zero of the polynomial in the numerator of our transfer function, and consequently the finite zero is at z1 is equal to minus 2. How about infinite zeros? Well, for rational transfer functions, the total number of poles or zeros must be equal if the poles and zeros at infinity are included. This means the following. Since we have two poles, we need to have the total of two zeros. We have one finite zero given over here, and we need to have one infinite zero. That zero will be denoted by z2, and it can be at plus minus infinity. We will see later. Next, let us mark or draw the poles and zeros on our diagram. Since we have two poles, I need to have two markers for the poles. Here's the first pole, and here's the second one. Both of them are at 0. How about the finite zero? The finite zero is given at minus 2. Consequently, my zero is located over here. And I can use a circle to mark my zero. Here it is. We have an infinite zero that can either be at plus infinity or minus infinity. We will see later on. So why are the zeros and poles of a transfer function so important? Well, we know that the root locus will start at poles and it should end at finite and infinite zeros. Furthermore, we know that the root locus is symmetric with respect to the real axis. For example, we know that the root locus will start from these two poles. It can go like this. This is the first branch, and since the root locus is symmetric with respect to real axis, another branch needs to go like this. Then we know the following. We know that the root locus, that is, one of its branches, will end at this pole. So this will be the end. And, of course, another branch should end in plus infinity or minus infinity, and we will see that later on. Next, we proceed with the step number 2. In step number 2, we construct the asymptotes of the root locus method. The asymptotes are centered at A, and I will explain the formula for computing A later on, and they're leaving at the angle BL, where L goes from 1, 2, 3, 4 until n minus m. Where m is the order of the polynomial in the numerator, and in our case it is equal to 1, and n is the order of the polynomial in the denominator, and in our case it's equal to 2. Consequently, we have a single asymptote, and that asymptote is centered at A, and it has an angle of B1. This is because L is only equal n minus m, that is, it's equal to 1. Okay, next, let us write a formula for A. The formula for A is given by A is equal to sum of poles of our transfer function minus sum of zeros of our transfer function, and we are only taking finite zeros, divided by n minus m. On the other hand, the formula for angle is given by BL, in the general case, is equal to 180 degrees plus 360 multiplying L minus 1 divided by n minus m. Where L takes the values of 1, 2 until n minus m. Okay, let's compute A and B1. A is equal to, let's see the sum of poles. We have two poles and both of them are zeros. However, we will still write 0 plus 0. Let's see, what do we have over here? We have minus sum of zeros. Minus, what are zeros? Let's see. We only have a single zero and minus 2. Consequently, we write minus 2. And we divide the complete expression with n minus m, and that's equal to 1. Consequently, we obtain 2. So our asymptote is centered at 2, somewhere over here. Good. Let's see the angle. Okay. B1, since L takes only a single value of 1, is 180 plus 360 multiplying L minus 1, and that's 0, divided by 1. Consequently, we have 180 degrees. Let us graphically represent that asymptote. I will just for a moment erase this part. Then I will expand my x-axis, or real axis, better to say, until here, and this is real now. The asymptote is centered over here. To better illustrate this asymptote, let's change the color. It's over here. And we know that the angle that this asymptote creates with the positive real axis is 180 degrees. Let's illustrate the asymptote for different degrees. Okay, so this angle over here is obviously, for example, 135 degrees. Good. By taking this fact into account, we figure out that our asymptote has an angle of 180 degrees with respect to the positive real axis. This is very important information. So we know that our asymptote looks like this. That is, the root locus when k goes to infinity approaches this asymptote. And if you remember what I said maybe 5 minutes ago, I said that we have finite and infinite zeros, and the locus should end in finite zero and in an infinite zero. And this asymptote actually shows the direction of an infinite zero. So we know that our root locus, or better to say, one of its branches will end over here. It will approach to this asymptote into infinity. And we know now that our root locus, or better to say, one of its branches will approach minus infinity. In order to keep this graph as clear as possible, I erased the previously drawn asymptote, but let's keep in mind that asymptote. And over here, I will just sketch the parts of root locus when we approach infinity. So we know that one branch will go here, and another branch should end at minus 2. That is, it will approach here. Perfect. However, what happens in between? We need to provide the answer to this important question. In step number 3, we investigate, does our root locus completely lie on the real axis? And here's how we investigate that. We start, for example, from this point. And in order not to destroy this graph, I will use a different color. For example, I will use the green color. We start from this point on the real axis. And we pay attention what's happening on the right side from this point. Are there any zeros and poles? There are no zeros and poles. Consequently, we will not have our root locus lying over here on the real axis. Good. Then we proceed further. We reach these two poles, we pass these two poles, and we are over here. Then we ask ourselves again, are there poles and zeros right from this point? Yes, there are. There are two poles over here. There are two poles over here. This means that this part over here does not belong to the root locus. Okay, keep in mind that. Now, here's the general rule. If the sum of zeros and poles on the right side from our test point is an odd number, then this segment over here will belong to the real axis. And that's very important to keep in mind. Again, to the right side of our test point, we need to have an odd number of poles plus zeros, and if that's the case, then this segment over here will belong to the real axis. Let's proceed further. And again, I will erase these 2 points and other things. Okay, we go further. We know that this complete segment does not belong to the root locus. And we come to this pole, actually to this zero, we pass this 0 and we are over here. Again, we ask ourselves the following question. Is the number of poles and zeros, that is the sum of poles and zeros, right from this point an odd number? It is, because we have 2 poles over here and we have 1 pole over here. 1 plus 2 is equal to 3, and consequently this is an odd number, meaning that this complete segment over here on the real axis belongs to the root locus. Or better to say, there is a root locus or a part of root locus that lies on the real axis, and this is very important. Okay, so let's sketch that part. Here it is. Here's the part of root locus that's on the real axis. Let's stop here for a second and let's analyze our current conclusions. First of all, we know that our root locus will start from here. It cannot go directly on the real axis to the left side, because we know that this part over here does not belong to the root locus. So this means that the root locus can go either like this, and we know the root locus symmetric, which means that we need to have another branch going down, or it needs to go like this. Or maybe it can go somehow like this, right? Or maybe other direction, maybe somehow like this. We need to investigate that. That's the next step. However, we know that somehow root locus doing something like this, going crazy, and then it somehow has to go here, right? At certain point. And you just need to make everything symmetric, so I'm just giving my best to make everything symmetric, right? This should be one branch, there should be another branch. They should somehow meet over here, right? One branch should end at this finite 0, and another branch should go to infinite 0. And we need to investigate what's happening over here. Let's erase everything and let's start investigating. In step number 4, we need to investigate the departure angles from the poles. That is, we need to figure out the direction of departure from this pole. Do we depart, for example, by following this direction and this direction, or we maybe depart like this, or we might depart in this way? We need to figure out that. To find the departure angles, let us make a small sketch over here. Here I will consider the most general case. Here's my real and imaginary axis. And let's construct a pole over here. Here I raised my pole since I need to make one important correction. In order to be consistent with my previous notation and with this graph over here, I need to denote the poles by axis. And here's my pole, denoted by x. I'm interested to investigate the departure angle of root locus from this pole, and consequently I need to sketch the departure angle. Here it is. Here's the departure direction, and I'm interested in this angle. I will call this angle h departure. Let us assume that we have several other poles and zeros on our graph. For example, let us assume that we have a 0 over here, and let us assume that we have 2 poles and that one pole is located over here and that another pole is located over here. Let us introduce the following angles. And for that purpose, let's change the color. This angle over here will be denoted by S. and I will introduce the index 1, since this is the first 0. If you have another 0, the angle will be S2. On the other hand, let us introduce the angles for the poles. Here's the angle H1, and I have another angle. This angle is H2. To summarize, we need to construct several angles. This is our departure angle that we need to determine. Then we have angles from our original pole to our 0, and we're looking at the angle with respect to the real axis, so this is S1. Then we have angles from poles to poles with respect to real axis, and they're denoted by H. Over here I constructed zeros and poles that lie on the real axis. However, let's consider the case when we have, for example, a 0 or a pole somewhere over here. That is, a 0 or a pole with an imaginary part. For example, let's consider the 0 over here. How to construct the angle? Well, very simple. We draw a line parallel to the real axis, and here's our angle. This will be S2. Okay, now we are ready to state the formula. And here's the formula. The formula is that Q, where the Q is the multiplicity of this pole, that is, the pole from which we depart, times this angle, H departure, DEP, and let me erase this not to confuse you and to keep the notation nice. Let's erase further. This will be H departure is equal to two sums. Sum SI, that is, the sum of all these angles from other zeros, minus sum of all the angles from the poles H1 and H2, minus 180 minus 360 multiplying G, where G is an index, and G goes from 1, 2, until the multiplicity of our starting pole, that is, until Q. Let's apply this formula to our case, and let's see what's happening over here. Obviously, we have two poles, and the multiplicity is equal to 2. Consequently, Q, that is this parameter, is equal to 2. We write 2 times H departure is equal to. Let's see the angles. Over here is the 0 located in -2. Here's the line connecting our two poles to this 0. And consequently, this angle, S1, is 0. That is, the case that we are considering is the pole located over here. And consequently, S1 is 0. So we have 0. Let's proceed further. We don't have, for example, a pole over here, or pole over here, or pole over here. That's correct. We don't have them, and consequently, this sum here will be 0. Perfect. And we have minus 180 minus 360 multiplying G, where G, in our case, goes from 1, and since Q is equal to 2, the second value is 2. Next, let's erase this general formula in order not to blur our graph or our sketch over here with too many details. And let's start substituting the values. We have two departure angles. Let's compute the first one. 2 times h departure 1 is equal to minus 180 degrees minus 360 multiplying g is equal to 1. And consequently, the result is the following one. H departure 1 is minus 90 minus 180, and that's equal to exactly minus 270 degrees. So what happens over here? The departure angle is minus 270 degrees, and that's obviously equivalent to what? Let's see from the graph. This angle here is minus 270, and obviously this angle is equivalent to this angle over here, right? And that's exactly 90 degrees. Perfect! We obtained one very important information. The first departure angle, departure 1, is exactly 90 degrees. And this tells us the following. This pole will move in this direction. How about the second departure angle? Do we need to compute the second departure angle? Well, the answer is we don't need to compute it. Why is that? This is because our root locus is symmetric with respect to real axis. So we expect that another departure angle will be minus 90 degrees, that is, another branch will go in this direction. However, let's verify that. We can quickly verify that by typing 2 times h departure 2 is equal to, let's see, minus 180 minus, what do we have over here? 2 minus 720, and from here we have that h departure 2 is exactly minus 90 degrees. Again, I made a few equivalent statements over here, since this expression is obviously minus 90 minus 360, however, that's equivalent to minus 90 degrees. And here's the second angle. Next, we need to compute, or better to say, to find the points where our root locus crosses the imaginary axis. Why this point or this step is very important? This is because the point where the root locus crosses the imaginary axis is the point where we lose stability. Let's illustrate that. We know that we start from here and we kind of go upwards and we go downwards. However, this is just the initial direction. We can have a root locus that's doing something like this. And we want to see if there is a point for which the root locus crosses the imaginary axis. And that's very important. You'll see that in this case, such a point doesn't exist except the point over here. Now, to find this point, we have to go back and to understand what is a root locus. Root locus is basically a plot of closed loop poles when the parameter k, that is the gain of the open loop transfer function, is varied. Our open loop transfer function multiplied by the gain is given by this expression k times w, and that's equal to k s plus 2 divided by s squared, where this parameter k is the parameter that we vary. For k is equal to 0, we are obviously at our open loop poles. However, as k is varying, the closed loop poles will vary, and the closed loop poles are given as the solution of the characteristic equation. And the characteristic equation is given by this formula. S plus 2 divided by s squared equal to 0. From where does this formula come from? Well, let's remember the basic structure of our controller. This is K. Our controller is simply a proportional term. Over here we have W. Then we assume a negative feedback until here. This is our reference, and this is our system. So the open loop transfer function is this part over here. The characteristic polynomial is simply the zero of the denominator of the closed loop transfer function. And the closed loop transfer function is obviously given by this formula. V closed loop is K times W divided by 1 plus KW. And here it is. Here's our characteristic polynomial. Here I will write again my characteristic polynomial, 1 plus K times s plus 2 divided by s squared. And this should be equal to 0. From this equation we obtain s squared plus ks plus 2k is equal to 0. Next, we need to investigate if all the zeros of our characteristic polynomial are strictly in the left half of the complex plane for positive values of k. If that's the case, our root locus will never cross the imaginary axis. So let's do that. There are several ways to do that. In my case, the most simplest way is to use the route criterion. Let's construct the route array. Here's how we do that. The coefficient over here is 1. So, first row of our route array is 1 and 2k. In the second row, we have k over here, and we don't have anything over here, and we can simply put 0. Next, let's construct the term over here. The term is constructed by multiplying this term with this term, and then adding a minus sign and multiplying these two terms and dividing the result by this term. Consequently, we have 2k, right? K squared, you should be careful. What do we have over here? We have 0 minus 0 divided by k. And as the result, we have 1, 2k, we have k, we have 0, and over here we have 2k. This characteristic equation has all the zeros in the left half of the complex plane if and only if the coefficients in the first column of our route array are always positive. And we can see that that's precisely the case for k is larger than 0. And this is a very important conclusion. This conclusion tells us that our root locus will never cross this point. And that's very important to keep in mind. So, we are safe. The closed loop poles will go in this way. Next, we proceed with step number 5. We need to estimate the locations of multiple poles, and we need to determine the approach angles. The procedure that I will explain for finding the locations of multiple poles will give a criterion that's only a necessary condition for multiple poles. And this is very important to keep in mind. The equation that we need to solve is the following one. Basically, we need to solve this equation. d over ds of minus 1 over w of s. Complex point s that satisfy these equations are the candidates for multiple poles. Keep in mind, the solution of this equation are only candidates for multiple poles. Further investigation is necessary in order to show that they are actually the multiple poles. So let's solve this equation. Let's see what we have over here. We need to compute the first derivative with respect to s of 1 over w of s with a minus sign, of course, and we have s squared divided by s plus 2, and that's equal to, and you can verify this formula later on, and keep in mind that I'm skipping a few steps in order to make this video short as possible, so I'm obtaining this formula, s plus 2 squared 2s squared plus 4s minus s squared, and this should be equal to 0. Consequently, we have the following expression: s squared plus 4s should be equal to 0. And this equation has two solutions: s is equal to 0 or s is equal to minus 4. These 2 points are candidate points for multiple poles. Let us investigate, are these points actually the points of multiple poles? Well, we immediately see s is equal to 0. Perfect. These are 2 poles over here. So in fact, this is correct. This is the first point of multiple poles. It's given over here. How about s minus 4? S minus 4 is given over here. And we expect that in this point, we will have multiple poles. And that's actually correct because we know from the previous analysis that this whole segment on the imaginary, or actually on the real line, belongs to the root locus. To remind you, this is minus infinity. And consequently, this is also the point of multiple poles. And we have actually 2 poles over here. Here, I need to mention one very important thing. 2 segments or 2 branches of root locus come together at 180 degrees and break away at plus minus 90 degrees. So what does this thing mean? Means that at this point over here, we have one branch coming from this side, another branch coming from this side, and they break away plus minus 90 degrees. So this one will break either in this way or in this way for 90 degrees. That is for this angle. And this is obvious since we know that the root locus needs to end at minus 2, that's the first branch, and another branch needs to end at minus infinity. And we are ready to construct our final root locus. For the time being, I will just erase this part since I want to keep this graph as neat as possible. And I will use a different color, for example, green color, to construct my point of multiple poles. Here it is. This is minus 4. And let's see what's happening over here. I start from here, from that point, and let's use the correct color. And I know that I cannot cross the imaginary axis, and I'm leaving with an angle of 90 degrees. Consequently, I need to go somehow like this, then I go down, and then I approach this point with an angle of 90 degrees. And beautiful. Here's our first branch. How about the second branch? Since the root locus is symmetric with respect to the real axis, I need to have one branch doing this. Here's the second branch. Perfect. Two branches come together at 180 degrees, that is, here's 180 degrees, and they break away at plus minus 90. Consequently, one branch will go this way, and another branch will go this way. Perfect. This is our root locus. The shape of this curve is irrelevant. It's mostly important to keep in mind that this curve will never cross the imaginary axis. That is, our closed loop poles will always be positive. And perfect. That was the procedure for constructing the root locus. Here I need to mention the following. In my previous tutorial, I explained how to construct the root locus in Python by using the Python control systems library, and here is the code. In order to make this video as short as possible, I will not explain this code. This code is thoroughly explained in my previous video, whose link is given in the description below this video. So watch this video. However, here, just for illustration, I will generate the root locus in Python in order to make sure that this graph is correct. So let's do that. Here's my transfer function, but first I will clear my Python environment. I will erase the workspace, and here's the transfer function. That's exactly our original transfer function. And let's construct the root locus. Here it is. Perfect. It's exactly the root locus shown over here. Okay, that will be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.